We have been looking at solving the Maxwell's equations, particularly the Poisson equation, which is a potential formalism, in terms of Green's function. And we have also looked at last time an example for the Dirichlet type of boundary conditions. We shall first look at another example today with the different types of different geometry of boundary, and then also have a look at the case of dynamics when phi can also be a function of time. So let's start. So this is my example 2. And remember that all that will change for a Green's function is the shape of the boundary. If the shape of the boundary changes, we are dealing with Laplace equations, we will get a different Green's function. Okay, and this is probably you have already done. So let us consider the shape, the boundary shape. Sphere. And the obvious choice of origin is at its center. So I call the sphere is of a radius a. So if you change the radius to anything else, so that a parameter that will come in your Green's function will change to anything else. Now what is the geometry of the problem? So I have this sphere, so I draw a circle which represents my sphere. And I have chosen the boundary here, the origin here. Okay. Mostly for this type of cases, you deal with an exterior problem, which means your volume is here outside the sphere, and one surface which is enclosing the volume is the surface of the sphere. The other surface may be at the infinity. You can also deal with an interior problem where you are dealing with the surface inside the sphere. Okay, so let's say exterior problem. So then you choose your point charge outside for the Green's function, and so that you can say that vector to be x prime. Conveniently, I have put my point charge along my x-axis. That is because I can choose the direction. That is absolutely which direction I call x, y, and z for the sphere. It's absolutely of my choice. I have chosen it as a horizontal direction now, and say this is my x. So I will always have to define an angle which is the angle between these two. So, or you can say that x cap prime dot x cap is cos of delta. Now I will leave it to you, because this probably you have already seen in your earlier courses. The Green's function in this case can be written in the following way: x minus x prime is nothing but x square plus x prime square minus 2x prime cos delta, and that entire thing to the power half. That gives you the magnitude. This minus, so let me bring it to a little more to the left. This minus, now because it's a sphere, this will be a little bit more involved. A is the radius of the sphere, remember. Okay, this is the Green's function if the boundary is a sphere, and delta is the direction. Delta is the angle between the direction of x and x prime. I have not gone through the detail of calculating this. This you will find in any book, and you know the method to do it. You should be able to do it for the sphere. Once I know this, I can calculate del g del x prime. Why I am doing this? Because remember, in the surface term of the Green's function solution had this thing, and this I have to calculate at the boundary. So that is x prime equals a. So it doesn't matter whether you write del g del x at a or del g del x prime at a, it will be the same. Just you have to replace x by x prime, because if you look at this Dirichlet-Green's function, it is always symmetric about x and x prime. If you change x and x prime in this expression, nothing will change. And then now I can write down for the case of sphere, if the boundary is that of a sphere, you have to be careful while writing the first volume integral, because that volume can be of the exterior problem where the volume is outside the sphere, or the interior problem where the volume is inside the sphere. Surface is always the surface of the sphere. See, the direction of x or x prime is towards the outward normal. So del g del n prime is nothing but the del g del x prime, which is written over there. So I just write it as del g del x prime. This is phi at a theta phi. So I write it in terms of polar coordinates. With the keeping it at the surface, which means x equals to a, r equals to a. Now let us say that, okay, so this is all kind of hypothetical so far. So let us solve a problem, an example, and you will see a few in your assignments. So if I say that, okay, so now I have a spherical boundary. So this is spherical boundary. It's grounded. I'm sorry, it's not grounded. So the potential is not zero, but somehow it is kept at a constant potential V0. Okay. And what is the condition on rho? No charges outside. So I have a sphere. Better be conducting, it will be easier. But anyway, I have a sphere which is kept at a constant potential V0. And I am seeking for an exterior solution of the problem, which means that I want to know what is the potential at any point outside. The origin I have chosen to be here. So I want to know what is the potential at x. X is outside the sphere. Okay, so outside there is no charge. So the first term is 0, rho is 0 everywhere. So phi x is entirely given by the second term, which is minus 1 by 4 pi. I can write this dA prime is the integral over the surface of the sphere, which is 4 pi a square dA I'm sorry. See the surface of the sphere. What is the volume element or the area element? The area element of the surface of the sphere is, so let us write it down. It's a square and then d theta and d phi. But there is a symmetry about phi, so that gives me directly 2 pi. And then I have sine theta d theta. This is just nothing but dA. So in any point here is a square 2 pi sine theta d theta. I have to integrate over theta. We'll see that if I choose a symmetry, my z axis about this, then there is a symmetry about phi. So I can directly do the phi integration. The phi will not appear anywhere. I will see that. I have not done it yet. So I am just going ahead and just writing that the phi integral is done. So that gives me a 2 pi. So the integral, only integral remains 0 to pi on theta. Okay. And better write d theta later because I have not written the integral yet. What do I have for the integral? Well, the potential is kept at constant V0 at the boundary, so that can go outside. And the I need that V0 goes outside, so this has gone outside as V0. So del G del X prime is what I have to write, which is given here. So A x square plus a square minus 2ax cos delta to the power half, and here I have a square minus x square and d theta. Okay, see it's cos delta over here, so I have to figure out what is that. That is not done yet. Now I have chosen my x like this, so which means that theta equals to 0. So the vector x can be written by x, theta and phi. X is the rho, theta and phi, so x is the amplitude of vector x, theta and phi are the directions. Similarly, x prime can be written as, so if I do that, we will agree that x cap is nothing but cos theta sine phi I cap. I is the x-axis of the horizon, one of the horizontal axis. I am sorry, so these are all going. So sine theta cos phi I cap plus sine theta sine phi j cap plus cos theta k cap. But what I have done is I have chosen my x cap along the k cap axis, so which means that theta is along the k cap axis, so x cap is basically k cap. X cap prime is sine theta prime cos phi prime So remember, cos delta was x cap dot x cap prime, and now I can write them in terms of all these sines and cosines. So I will get sine theta cos phi, sine theta prime cos phi prime in the first term. But you see that these terms are 0, so I will just get this. So I will get cos theta times cos theta prime. Cos theta is 1, so this is essentially cos theta prime. So when I do this dot product, I have chosen theta to be along the k direction. So theta is essentially 0 degrees. So sine 0, theta is 0. This sine 0 is also 0. So these and these terms are 0. This terms is 1, so this gives me just k cap. So when I do the dot product of x cap with x cap prime, the first I cap and j cap does not give me any contribution. The only contribution comes from k cap, and that is just cos theta prime. So which means now, so these are all theta primes, I'm sorry, because we are doing the integration on the prime coordinate. So this cos delta can be replaced by cos theta prime. So finally, I get my phi x, which is, let's see what has happened here. So that's 2 pi can cancel out. A square will give me a. So this is minus v0 a by 2. This is not x prime. I think that is the integral. Okay. So please verify. Please check. And also do the integral. If you do the integral, you will see this will come out to be something very familiar. So that I will not do, but just wanted to demonstrate to you how this works. So in this particular case, it was all contribution came from the surface term, though there was no charge inside the volume of concern, that is the exterior volume. All the contribution came from the fact that there is a spherical surface where a potential is kept constant. Okay, so that is the essence of the way of solving electrostatics and magnetostatics problem using the Green's function technique. Let me go a little bit to discuss about what happens in electrodynamics. And this is going to be a very, very superficial discussion. But if you have got the idea, then you will be able to figure it out. So in the electrodynamics, we looked at this operator, which is 1 by c square del 2 del t2 minus grad square. So all that I have to do now for the case of electrodynamics and Lorentz gauge that the problems in electrodynamics in Cartesian will look like the following. It will have this form. You see, if I want to come to statics, everything, the t dependence goes away from everywhere, and in the box square operator, the first term goes away, so the left hand side becomes minus grad square psi. So that's essentially again the Poisson equation. Now for this corresponding equation for Green's function, we know how to write down. All that I have to do is I have to change this to the Green's function. Now this will depend on x t, x prime t prime, and in the right hand side I will have 4 pi x minus x prime t minus t prime. The rest of the method is exactly the same. First you have to solve for the case of the same equation with, here remember that I have not chosen the boundary. So what is about the boundary here? So it's a boundary is not only that you have to tell about a volume, you also have to tell that when you have measured the potential on that volume. So the boundary is measuring the potential on the surface of a volume at a given time. If I don't tell the time, or it's actually the time interval, so in between this time and that time, the variation of the potential has to be known at the boundary. If that is given, then this problem can be solved. And remember that also, so you are talking about a volume, you are also giving a time interval. So it's a volume, the surface which is surrounding this volume, and this you assume to be a clock, then you are saying that between this time and that time I am given every information inside the volume and on the surface. So then only I can solve this problem. Okay, that is about the boundary condition. And what will you do that? So well, first you will say that okay, I will throw my volume to be infinity, consider all times, and then I solve this equation and call that G prime. And that G prime, you can again use the Fourier transform technique to get the G prime. The integral is a little more complicated in this case. This comes out to be the following. It has the classic x minus x prime in the denominator, but the numerator now involves time. So the numerator is a delta function. It's a little complicated delta function. It's t prime minus t plus minus, or rather minus plus. So there are two solutions to this. So I call those G plus minus. So when you take the plus, you have to take minus from here. Okay. So what is the interpretation? The interpretation is that t prime has to match with either t minus that or t plus that. Okay. So if I want to figure out what is psi at a given x and t, now see this has two terms. So one is the surface term which I am not writing here, you can assume that surface term to be 0, throwing the surface at infinity. But then I have plus this term as the, this is how I write the solution once I have got the Green's function. And what I am saying is that the Green's function is for a problem where my boundaries are at infinity. So then this is equals to, I can do the t integral because I have a delta function over there. So what happens when I do the t integral? This remains as it is, but rho now has to be evaluated at some t plus minus, where t plus is given by t minus, remember that the left hand side is a function of t, so it should be given by t minus x prime by c, and t minus is given by so this is called advanced solution and this is called retarded solution. So what is happening here? Let's see. So I have the charge density. So I am asking the following question. So I have one point here, say at x, another point here, say at x prime. X prime I have a charge, so that I call rho at x prime. Okay, it's also a function of t, so let's call that t prime. I'm asking the question, what is the potential at phi? So at time t. What this is telling you is, you see, this is the exact same looking case for the electrostatic solution. But there is the fact that this rho has to be calculated at an earlier time. What does it mean? Well, if we calculate the distance between this point to this point, this distance is mod of x minus x prime. And the time a light signal takes to go from x prime to x is given by x minus x prime by c, because c is the speed of light. So what it is telling you is that to know the phi here, you need to know what is rho, which was there this much time earlier. So that is, the effect of this rho is felt at this point at phi, for phi at a later time. So that's why it's called a retarded or later solution. Okay. There is also an advanced solution, as you can see here. It was used by Wheeler and Feynman to explain certain things, but finally it did not work out very well. So we'll not even talk about it. But this is the meaning of the retarded and the advanced Green's function. Now this can be used now to solve for electrodynamics problem, particularly the problem of propagation, generation and propagation of radiation. But that's it. That's all that I will discuss with you in this course. And I have also uploaded the assignments, so please go through the assignments. What we have done today is looked at the electrostatic Green's function and looked at it for two different boundaries and kind of sketched how we solve the boundary value problems with the Green's function. What is its connection with the method of images? We also looked at very briefly the Green's function for the electrodynamics problem how what is the equation that you solve to get the Green's function, what is the solution that you get, and what is the